Hi Victorians. We're going to go through the final points of the reactions of alkyl halides or halogen derivatives. I believe that I can plug in some knowledge gap in your understanding of the reactions, and there are some fine things for you to take care of when it comes to answering exam questions. Okay, so I'll just dive straight into the mechanism, because once you understand the mechanism and how everything works from the mechanistic point of view, you are going to be able to answer many questions that affect the reaction. The mechanism for reaction for alkyl halides is mainly the substitution reaction and also the elimination reaction. In the context of A-level assessment, we are going to just focus on the substitution reaction. Elimination reaction mechanism is not tested in the A-level exam. I will go through the SN2 reaction first. The SN2 reaction stands for, the S stands for substitution, and the N stands for nucleophilic, and the 2 stands for bimolecular. I have an alkyl halide here. It is an iodomethane in which the whole molecule is characterized by the Ci bond over here, the Ci bond over here. Okay, so what you want to really focus on are two things. Okay, two things you need to focus on when you are looking at a substitution reaction. In this case, it is a SN2 reaction. It means that the rate of the reaction depends on both the concentration of the nucleophile and the concentration of the substrate, in this case the alkyl halide. And the factors that affect the attack of the nucleophile on the electron deficient carbon over here is very important. Okay, first of all, I have a Ci bond here. The factors that determine whether this bond or this CX bond will break is very important. The strength of this CX bond will determine the rate of the reaction. So for example, if I replace the iodine with a chlorine, or I use a CCl rather than a Ci, okay, the rate of the reaction, if the atom here is a Cl, would be slower. Yes, slower. Okay, slower than if it is a iodine, because a CCl bond is stronger than a Ci bond. Okay, so there is one factor you got to realize. Okay, so since this is a substitution reaction, the OH group over here is going to replace the I over here. Okay, so you can see that the OH over here has replaced the I here. Okay, and we give this I a name. Is called a leaving group. It is a leaving group. For the SN2 mechanism, it would be great if you can visualize everything in terms of 3D. we always draw the delta positive carbon over here in a tetrahedral configuration to show a very open space between the hydrogen, 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 carbon. We want to leave a very open space here because in reality that space allows the nucleophile, in this case the OH minus, to come in from the back. This should be going on in your mind. Now when the nucleophile comes in, the orbiter of O in the OH minus is going to overlap with the C, the carbon in the substrate. And when that happens, the Ci bond actually breaks off, taking away the Ci original shared electrons, okay, to give the product over here. In the middle of the reaction, we have a transition state. Okay, so this transition state is an imaginary state which chemists thought of so that we can have an explanation for why the product turned out to be like this. If you can look at the structure of the substrate and the product carefully, you will realize that there is an inversion going on. There's an inversion going on. Can you see that the OH here is in the opposite position of the I? Now if the I originally is here, the I originally is here, right? But now the OH has become on the left hand side, right? But of course this is a very simple molecule. Even though there is an inversion, we can't really see it because the H here and the H here and the H here are the same, so we can't really see an inversion here. Okay, but you need to know that if the groups are different, you will end up with a chiral compound, and then we will be able to see the inversion happening. Okay, so in this case the rate is second order overall and is proportional to the concentration of the alkyl halide and the concentration of the nucleophile. Okay, if we look at the energy level diagram, okay, just to link up your knowledge, we have a transition state at the top of the energy profile diagram. Okay, and this represents the dotted line represents the partial bond. The green dots over here represents the partial bond that is about to break between C and I. The blue dotted lines here represent the bond that is about to break between, the bond that is about to form between the O and the C. And overall, this is an exothermic reaction. Exothermic reaction. So over here, we have the orbital diagram, okay, the electron density orbital diagram. So you can see that the radar, the more red the diagram, it means that the electron density in that area is higher. So this is a CH3I. Can you see that the iodine, because it is more electronegative than carbon, it is acquiring most of the electrons? It's because it's redder. Okay, and over here the OH minus, this one is the oxygen. Because it is more electronegative than H, it is acquiring most of the electron density in the whole ion. Therefore, the one at oxygen over here is redder than the portion at the hydrogen over here. And over here, you can see the bonds forming and breaking. Okay, over here, this is breaking, and over here, this is forming. Okay, so just this is breaking, and this is forming. Okay, and this one shows, this diagram shows the I minus that has formed from the breaking of the Ci bond. Okay, so these are the things that you need to know. You need to link up your knowledge between energy profile diagram and also the reactant structure. The reactant structure. Oh yes, there's one more thing I need to tell you. Can you see that this HHC is actually planar? Okay, they actually form a plane. Okay, these four atoms here, they actually form a triangular plane. Okay, and this OH minus or OH delta minus and I delta minus actually is below and above the plane of these four atoms.